Hi, we're back with the remaining part of the recording that concerned GFR. And where we had stopped is we had stopped at right here where I was talking about if you decrease that glomerular capsular hydrostatic pressure, that could decrease GFR. And then I said, well, if your mean arterial pressure dropped, that could decrease that pressure. And we said, well, it's only a small amount due to this thing called autoregulation. Well, autoregulation literally means self-regulation. This is a local type of regulation, and this in the kidneys is very strongly autoregulates. The whole purpose with autoregulation is despite changes, relatively big differences in your mean arterial pressure, is that we keep GFR relatively constant as well as renal blood flow. And so if you look at this picture, as you'll notice for a very large range of your mean arterial pressure, so you see from 80 to about like 180 millimeters of mercury, is that GFR pretty much is constant, as well as you notice the renal blood flow. Now if you notice the picture, you see this big diameter thing here and a smaller diameter. What that's trying to depict is what's happening to blood vessels. And so, which would be important in autoregulation. So if you think about it, if my blood pressure dropped, my glomerular hydrostatic pressure would drop, my filtration would drop. I don't want that because the kidney needs to get rid of waste products. It needs to maintain an adequate filtration rate. Well, what would happen is if that dropped, I'm like, I don't want that. I want to have more flow. And so what you'll see is blood vessels will dilate. And we're talking specifically there in the kidneys. And what's going to, that's going to allow more blood flow into the glomerulus and allow us to maintain an adequate pressure. If you have an increase in pressure, that would increase filtration rate. I don't want too much. I want it in a nice narrow range. Plus, I don't want that pressure too high because it could damage the capillaries or the glomeruli. And so what happens in the process of autoregulation is the diameter of these vessels are going to decrease, which would get flow back to where it's supposed to, and keep GFR at a relatively constant level. So autoregulation is accomplished by altering diameters of the afferent, efferent arterioles and your glomerular capillaries. And specifically, I want to address kind of what's going to be going on, is because this is kind of important. Is I want to address the afferent and efferent arterioles. So the afferent arterioles are the feeder vessels. So remember they're larger in diameter. So, and then you have your efferent arterioles that are past the glomeruli. Remember, those are smaller in diameter, and they keep that pressure high so you can have an adequate filtration rate. So what's going to happen is through a number of different processes, and we're not going to go real in depth here, is what we want to happen is if your mean arterial pressure drops, I want the afferent arteriole to open up, and because that's going to allow me to have more flow. And I want a little mild sorry, I don't even want to draw on that. That's not good. Is I want the efferent arteriole to constrict somewhat because that's going to allow me to have a better pressure. And it would be the opposite of what we have over on this side. Now I'm going to go back to that thing, and I'll draw some more pictures in a second. Is there's actually two theories by how we have autoregulation, that despite these changes in your mean arterial pressure, that GFR stays relatively constant. And one of the theories is a myogenic theory having to do with the muscle. So remember, smooth muscle of blood vessels will, if they stretch, automatically will contract. So if filtration gets high, the vessels that are feeding the glomeruli are going to constrict with decreased flow. And then if pressure's too low, that muscle actually relaxes, and that you see something like this. Another theory, and I'm going to have you go and review it on your own, is something called the tubuloglomerular feedback mechanism. So this is a mechanism by which the tubules, the renal tubules, and specifically the macula densa cells that are in those early proximal tubule, which is part of the juxtaglomerular apparatus. And I had previously have talked about that, is that juxtaglomerular apparatus is very important in maintaining GFR. Well, there is a theory by which the macula densa cells that are located in that early distal tubule are sensing changes in sodium levels in that fluid, that tubular fluid, which would be affected if your filtration rate was either increased or decreased. And it will sense it and sense what has happened and cause some changes with these cells. Will talk to the juxtaglomerular cells, which are located in the afferent arteriole, and say, hey, either GFR has gone up or it's gone down. I need to keep it at a constant level. So you need to do something. It's going to, and then what it'll do is it subsequently will ultimately, and I'm being very vague, affect what's going on in the smooth muscle of the afferent and efferent arterioles. So I'm just going to leave it at that for this point in time. So I want to come back here because it was something I was starting to talk about, is these two. These two are hands down the most important means by which we physiologically regulate your GFR, is changing the diameter of the afferent or efferent arteriole. So you'll notice on the top one it says if I decrease the resistance of the efferent arteriole, that means that efferent arteriole has gotten bigger. Say it's gone from here to here. It's opened up. Well, remember that was important. Having that little bit smaller diameter was very important in maintaining that high back pressure that you have in the glomerulus. And so if you open those up, that pressure is going to drop. And if that pressure drops, GFR drops, will decrease. If I increase the resistance of the afferent arteriole, what's going to happen is you're going to end up with a smaller diameter. And so remember, the afferent arteriole is the vessel that's feeding the glomerulus. So if you constrict that, that pressure there now in the glomerulus is going to drop, and that would also decrease GFR. And so you notice that some things could affect the diameter of those. And one of the big things is to think about angiotensin II. So angiotensin II does a lot of things. And one of the things it does is it preferentially constricts the efferent arteriole. Write that down. It preferentially constricts the efferent arteriole. If it does that, that will actually increase your GFR. But if you decrease angiotensin II levels, that would cause that vessel to open up and GFR would drop. And actually, angiotensin II, hands down, I'll write this down, angiotensin II, hands down, is the most important means of regulating GFR because of its effects on that efferent arteriole. But we'll notice is some other things that could affect the resistance of, you notice the afferent arteriole, the effects of the sympathetic nervous system, which is what we're going to talk about very shortly. And another thing would be endothelin and norepinephrine. So remember, endothelin is released by damaged blood vessels. It's a vasoconstrictor. That would be important if you wanted to minimize loss of blood from the body, and you get constriction of the blood vessels in the kidneys. Norepinephrine, that's a vasoconstrictor, so that can be released by the sympathetic nerve endings or also from the adrenal medulla, and that would act as a would constrict the afferent arteriole, which would decrease GFR, which could happen, say, during exercise, is we do have a little bit less blood flow going to the kidneys during exercise. So those are some of the things that could affect it too. So let's just look at, actually here, I'm going to go back here so you can see this. So as a reminder, the juxtaglomerular apparatus is these macula densa cells that we have in the early distal tubule, and it's early distal tubule. And these juxtaglomerular cells, which are smooth muscle cells, this collectively is the juxtaglomerular apparatus. So that's extremely important in the regulating of GFR. And it's that tubuloglomerular feedback mechanism that's going to be very crucial in it. I may make just a separate recording just to kind of address that for you, but this is extremely important in it. These juxtaglomerular cells produce renin, and that's going to play a role very shortly. So let's look at that role of the renin-angiotensin-aldosterone system. You've seen this many, many times before. So, for example, if you have a decrease in your blood pressure or a decrease in blood flow to the kidneys, what's going to happen is the juxtaglomerular cells, which are really baroreceptors, they're going to detect that pressure is dropping. It does not like it. Since I need to maintain an adequate pressure for filtration, so it's going to cause renin to be released into the bloodstream. And ultimately, I'm going to just jump to the end, ultimately that's going to keep GFR adequate and keep it from dropping. And so what you'll notice is renin converts angiotensinogen to angiotensin 1. Then angiotensin 1 is converted to angiotensin 2 using the enzyme angiotensin converting enzyme, which we have high levels in the lungs, but it's found in other tissues too. Is the angiotensin 2 has a number of different roles in the body. So you'll notice vasoconstriction, increased aldosterone secretion, increased ADH secretion, increased thirst. So let's kind of just go over the main things that's going to happen in the kidneys. So first of all, though, again, renin is released by the juxtaglomerular apparatus in response to either a decrease in your blood pressure or blood volume, because a decrease in blood pressure or blood volume could drop your glomerular blood pressure. So it restores that blood volume and blood pressure through a number of different mechanisms. So one of the things here, I'm going to address this one, is it vasoconstricts the efferent arteriole. And so remember, if you constrict that, that helps to increase that glomerular pressure. It also is because of its effects on aldosterone. Aldosterone will result in more sodium being reabsorbed, and if that part of the nephron tubule is permeable to water, that also will increase your blood volume and help to increase your blood pressure. Now, one thing that's actually not here, and we're going to write this down, is angiotensin 2 also directly stimulates, stimulates sodium reabsorption in the proximal convoluted tubule, so PCT. Now, that proximal convoluted tubule is also permeable to water. So if you have more sodium being reabsorbed, water is also reabsorbed too. So it specifically is affecting the proximal convoluted tubule. Aldosterone targets the late distal tubule and the cortical collecting tubule. So, but also its effects on thirst and increasing ADH secretion, those ultimately will help in getting blood pressure back up and blood volume back up. The autonomic nervous system also can affect GFR. You don't have innervation by parasympathetic fibers. It's all sympathetic, and the fibers are coming from the inferior mesenteric ganglion. And the sympathetics cause very if you have strong parasympathetic, or sorry, sympathetic stimulation, you get vasoconstriction of afferent arterioles. And so remember, those are your feeder vessels. So remember, you got afferent, here's my glomerulus, here's the efferent, a little bit smaller. If this is smaller, I'm not going to be able to have as much blood, not enough pressure to have that filtration that takes place in the glomerulus. So that decreases GFR and slows down the production of filtrate. This would be definitely kind of, let's tie it into where this is extremely dramatic, is with the Cushing reaction or with the CNS ischemic response. So remember, with those, you had problems with perfusion in the brain, and so it triggers a very strong mass sympathetic response where you have a very strong constriction of blood vessels throughout the body, even in the kidneys, and that would decrease GFR, which in the long run is not so good if it's significant. But you do have, let's say during exercise, it's not going to be the fact that you're not going to be able to get rid of waste products, but you'll have somewhat decreased blood flow to the kidneys. But we will, don't worry, filtration will, there's other mechanisms in place to keep the, if there's too much constriction, local controlled blood flow takes over. Remember, we talked about the local controlled blood flow, and that will open those vessels up so we get perfusion, but then will constrict again. So we do have things, protective things, if it's constricted for too long. So this is going to be the last part of the GFR, or glomerular filtration, for renal physiology. Another recording will cover specifically reabsorption and secretion.